I'll report results from my recent paper on the archive, the same title as the talk, Trace Dynamics and Division Algebras Towards Quantum Gravity and Unification. Here are the key points in the paper. We propose a Lagrangian for unification of Lorenz symmetry with the standard model in the theory of trace dynamics at the Planck scale. We argue that gravitation is an emergent classical phenomenon. It should not be quantized. What should be quantized is the Lorentz symmetry. Particles are described by bosonic and fermionic Grassmann matrices living in an 8-dimensional octonionic space. At the Planck scale, evolution takes place in the absolute cones time. Algebra automorphisms unify spacetime diffeomorphisms and internal gauge transformations in the 8D octonionic space. The symmetry group for the unified theory is the automorphism group of octonions. It is the Lie group G2 for electrocolor of one generation of fermions, F4 for electrocolor plus Lorentz-Weak, and 3 fermion generations. The electrocolor symmetry is unified with the Lorentz-Weak symmetry at the Planck scale, building up on the earlier work of Cohl Furey. Okay, what is the motivation for this project? To develop a formulation of quantum field theory which does not depend on classical time. So the starting point is really quantum foundational. Classical time is part of space-time geometry and macroscopic bodies, which are all classical, and that kind of a structure is a limiting case of quantum field theory, and we would not like the theory to depend on its own limit, and that's the reason for asking for a reformulation of quantum theory which is devoid of classical time, and doing so actually leads us to a quantum theory of gravity and a proposal for unification. The methodology for removing classical time from quantum theory is to raise classical space-time points to the status of operators and matrices. Just as during quantization we make C-number degrees of freedom into operators, we would like to do the same for space-time points. To do this, we start from Stephen Adler's theory of trace dynamics and generalize it to incorporate space-time points as matrices. Okay, let's first recall what is trace dynamics. Adler's theory of trace dynamics was proposed in the 1990s. It is a Planck scale matrix dynamics, although for simplicity, space-time itself is assumed to be 4-dimensional Minkowski space-time. And the idea is, given a classical Lagrangian dynamics, raise configuration variables and momenta to the status of matrices. Let's look at this example. Suppose there was a classical Lagrangian q dot square minus q square raised to an action by integrating over time. Those are C numbers. Q is a C number. Now we replace Q by a matrix. So Q hat is a matrix. Q hat dot is like the velocity of the matrix. Q hat dot square minus Q hat square. This is now a matrix polynomial. We take its matrix trace, integrate it over time. I get the action. This is what you call the trace Lagrangian of the matrix dynamics. And if you wanted to do it in the continuum limit for a classical field theory, you could do that too. At every spatial point at a given time, replace the field degree of freedom by a corresponding matrix. If it was phi of x, make that into a matrix and again take the matrix trace and now integrate it over the space-time volume to get the trace Lagrangian for the field theory. And once you have integrated it over the volume, you get the action. What is the motivation for doing this? It's a more general way of doing quantum theory. We do not quantize and set the commutation relations to quantum commutation relations. We allow them to be arbitrary. So matrix dynamics is what you could call a true quantization from which quantum theory emerges as a special limit. So given this trace Lagrangian, we can employ what is known as a trace derivative to differentiate with respect to matrices. This tells us how, given a trace of a matrix polynomial, how can I differentiate it with respect to a matrix to get the Euler-Lagrange equations of motion. So it's a variational principle like always, except that now I will vary with respect to this matrix Q. The end product is Euler-Lagrange equations. So these are basically matrix dynamics analog of classical dynamics. There is a Lagrangian formulation and equivalent Hamiltonian formulation. What we must note now is that these dynamical degrees of freedom, which are now matrices, they do not commute with each other. So QP commutator, for example, is not a constant. It is determined by the dynamics. Okay. Is it just this? Is matrix dynamics, trace dynamics just this, that we raise C number degrees of freedom to matrices? No, that would be quite dull and uninteresting. What have we gained? We have gained a great deal, in fact. So it turns out that, let's look at the Lagrangian again. Because it's a trace, you can make unitary transformations on individual degrees of freedom. And it is easy to see that because of the fact that we can make cyclic permutations inside the trace, this object is invariant under unitary transformation. So the trace Lagrangian is invariant under unitary transformation. So is the trace Hamiltonian that you will make from here. A result of this global unitary invariance is that there is a conserved charge known as the Adler-Millard charge, given by this following form. This is a theorem. The sum of the commutators Qi, Pi over all degrees of freedom is conserved. So the individual QP commutator is not conserved, but the sum is conserved. And this is very insightful, because what's happening in quantum theory is that the individual commutators are all constants and equal to IH bar. Here that's not true. Only the sum is conserved, as if various degrees of freedom are exchanging action. The QP commutator has dimensions of action. So the various dynamical variables are exchanging action with each other, whereas the total action is a constant. From here, quantum theory will emerge in that approximation below the Planck scale, where we have coarse-grained over scales much larger than Planck length or Planck time, say. Then the charge gets equipartitioned and every component becomes equal to the other component. The total is a constant. Individual commutators also become constants, and we set that constant equals IH bar. That's the definition of Planck's constant in the theory. So, but that will come. That's emergent. At the Planck scale level, the dynamics has this conserved quantity along with the conserved Hamiltonian. So in the theory, since we want to describe bosons and fermions, the degrees of freedom with which we work in the Planck scale trace dynamics are complex valued Grassmann matrices. The entries to these Grassmann matrices are complex valued Grassmann numbers. We know that Grassmann numbers can be divided into two categories: even grade and odd grade. So here's a typical example of the trace dynamics Lagrangian that we'll work with. A dot denotes time derivative with respect to this time tau, which we'll define, so-called Cohn's time. The Cohn's time we need when we include gravity. Right now we are just doing Minkowski spacetime, so this is ordinary spacetime, the time of ordinary spacetime. A subscript B on Q denotes a bosonic Grassmann matrix. Grassmann matrix whose entries are even grade Grassmann numbers. And you know, these have properties that bosonic Grassmann matrices have entries, and those entries commute with each other. And then we have fermionic Grassmann matrices. So QF will be a fermionic Grassmann matrix made of entries which anticommute with each other. And beta 1 and beta 2 are two constant fermionic numbers, complex fermionic numbers, which we will see in the theory repeatedly. So what's the kind of form the Lagrangian is having? It's a byproduct QB dot plus beta 1 QF dot dagger into QB dot plus beta 2 QF dot dagger. L is a length scale which is measured in units of Planck length, which is associated with this degree of freedom. And take a trace of this polynomial, integrate it over time. That is the action in trace dynamics. And here is the conserved Adler-Miller charge. If you have fermionic degrees of freedom, then you get the anticommutator QF-PF, where PF is the canonical momentum which we can get from this Lagrangian, and the commutator of QB-PB and their difference. And if there are many degrees of freedom, sum over all of them. This is the essence of trace dynamics. And again, now we raise this question, why do we do it? Why do we make a matrix dynamics? As you would notice, in going from classical dynamics to trace dynamics, we have skipped quantum field theory altogether. This was C number physics. There's no commutator. The QP commutator is just 0. Here we have matrices as dynamical variables. The QP commutator is not a constant, it's dynamically changing. And somewhere in between here is quantum theory. So quantum theory is emergent from trace dynamics, and let's see in what sense we recover quantum theory as well as the classical limit from trace dynamics. So what is the emergent dynamics if we are not observing at Planck time scales? There is variation happening on Planck time scales in this matrix theory. But suppose we are at lower energies. We observe, let's say, over time intervals which are of the order, say, 1000 Planck times. We have to coarse-grain the theory. And how do we find the coarse-grained dynamics? We employ the standard techniques of statistical thermodynamics to find out the emergent average dynamics. We know that at the coarse-grained level also the Adler-Miller charge and the Hamiltonian is conserved, and we allow, as in statistical mechanics, all possible underlying trajectories which are consistent with having a particular predetermined value for the trace Hamiltonian and for the Adler-Miller charge. So note that unlike what we usually do in statistical mechanics, say for a kinetic theory of gases, we do not necessarily have a large number of degrees of freedom. We can have just one degree of freedom as described, say, by this action. What we are asking is if we make many copies of this degree of freedom which follow different trajectories in the phase space, we are asking if we coarse grain over all those trajectories, what is the resulting dynamics that we will see. So it turns out there are two limiting cases. If the underlying Hamiltonian has a negligible imaginary part, so we must mention that in general this Lagrangian is not self-adjoint, and that is important. It's important, in fact, for the unification theory that we will arrive at. It is also important for recovering the classical limit, but it's not as if we, in an ad hoc way, by hand, have added imaginary part. This is the structure. This structure, you can see, is very harmonious. It's bilinear. And the first part is essentially the same as the second part, except beta 1 and beta 2 are two different odd grade Grassmann numbers, and that is what forces the Lagrangian to not be self-adjoint. Okay, suppose the anti-self-adjoint part of the Hamiltonian is negligible, then in the emergent theory at length scales much larger than Planck scale, we get quantum theory and quantum field theory out. We get quantum commutation relations because the Adler-Miller charge gets equipartition, and the underlying Hamiltonian equations of motion become Heisenberg equations of motion for the statistically averaged matrices. So we have trace dynamics matrices. In quantum theory, we have operators for as dynamical variables. We identify the statistically averaged matrices equivalently operators with the corresponding operators in quantum theory. So we make a map between the average trace dynamics and quantum field theory. So we must remember the underlying trace dynamics is not the same theory as quantum field theory. It's more general. It contains quantum theory as a special case which emerges after coarse-graining if we are not observing Planck scale dynamics. If we are observing Planck scale dynamics, we have to use trace dynamics, not quantum field theory. So I said there are two limiting cases for the average dynamics. One of them is quantum field theory. But there's a second limiting case. If the underlying trace Lagrangian has a significant anti-self-adjoint part, then the self-adjoint part of the trace Lagrangian collapses to the classical operator Lagrangian, and this process is known as spontaneous localization. So let's dwell on this a little bit. The concept of entanglement is there also in trace dynamics at the Planck scale. Entanglement is a feature more general than quantum theory. It turns out that for an individual degree of freedom, the imaginary part of the Hamiltonian is ignorable so long as the associated length scale L is much larger than Planck length. So we associated L or area L square. If this is much larger than the Planck area, the imaginary part of the Hamiltonian is negligible for 1 degree of freedom. But suppose many degrees of freedom get entangled with each other, the effective L then goes down. And if you entangle sufficiently many, L goes down to below Planck length, and this object becomes large. As a result, the imaginary part of the Hamiltonian also starts showing rapid variations on length scales larger than Planck length. So one way to visualize this is think in terms of Compton wavelength. If the mass of the object is very small, the associated Compton wavelength is large. It will be much larger than Planck length. But suppose we increase the mass so much that it becomes larger than Planck mass, then the associated length scale L will go below Planck length. So if there is a critical amount of entanglement taking place, then the imaginary part of the Hamiltonian becomes important. It essentially causes decoherence. It forces the self-adjoint part to one of its eigenvalues. Suppose you had something like trace q square in the self-adjoint part. Trace q square will now be sent to just one of the eigenvalues, say q square, the ith eigenvalue, qi square, and that represents the classical Lagrangian. The trace Lagrangian collapses to the classical Lagrangian, shouldn't say operator Lagrangian, classical Lagrangian, which is determined by the eigenvalues. So this is how the trace is lost. You lose the trace and go back to the classical theory you started from as a result of spontaneous localization, provided adequate decoherence is taking place. So you recall we started from the classical Lagrangian, we raised degrees of freedom to the status of matrices, and we took the trace. Spontaneous localization or effective decoherence sends the trace back to the classical value. So we do not have to recover classical limit by means of some interpretation of quantum theory. Rather, the classical limit arises dynamically. This is the same process as the Girardi-Rimini-Weber theory of spontaneous localization, but we are not putting it by hand. We are not modifying quantum theory for enabling collapse or spontaneous localization. We are starting from an underlying theory which unification requires us to keep as not restricted to self-adjoint. So that's a property of the unified theory. The Hamiltonian will generally not be self-adjoint. If it is, if the imaginary part is negligible, the coarse-grained theory is quantum theory. If the imaginary part is significant, the coarse-grained theory is classical dynamics. So as I said, the anti-self-adjoint part causes decoherence in the self-adjoint part. When we are back from matrices to C numbers, we could go back 2 slides maybe. Yeah, so you could look at this. If you remember this action principle made from a trace Lagrangian, spontaneous localization will send this back to the classical dynamics. And the classical dynamics will again be Hermitian, because what is the anti-Hermitian part doing? It is the one which is playing the role of the environment and inducing classicality. So we never see the imaginary part really, because we don't see it in quantum theory, because the Hamiltonian is by definition Hermitian. We don't see it in the classical physics because the imaginary part, so to say, is active, say, in the background, keeping these macroscopic systems classical. So it's hiding. The only way to really see the imaginary part of the Hamiltonian in action is to probe at the Planck scale. At energies lower than Planck scale, we will never directly test the imaginary part, be it in quantum theory or classical dynamics. So that's all we need really from trace dynamics. It's a matrix dynamics taking place at the Planck scale, and space-time is kept Minkowski flat. There's no gravity. There's no gravity in Adler's trace dynamics, but it is what I call a true quantization, which contains quantum theory within itself as a coarse-grained emergent approximation. Okay, so now we are ready for the second part of the talk, from where we move towards unification. How to incorporate gravity in trace dynamics using Alan Cohn's non-commutative geometry program. That will lead us to what we call generalized trace dynamics. Generalized trace dynamics is Adler's trace dynamics with gravity incorporated. And why do we want to do that? Because we want to have a formulation of quantum field theory without classical time. It will be a quantum theory of gravity. And we said for doing that, we have to raise space-time points to the status of operators equivalently matrices. So that was the philosophy of trace dynamics. Take a classical theory, raise C number configuration momentum degrees of freedom to the status of matrices. So we have to identify degrees of freedom in classical general relativity, which we can raise to the status of matrices. But so of course the most obvious degree of freedom is the metric, but it is already the metric is a matrix. We can make a matrix of matrices, but turns out that there are serious difficulties in that. So we will find a different route out. Before we go there, let me point out a very useful and instructive parallel between non-commutative geometry and trace dynamics. So we'll see the philosophy that if you want to do dynamics of a particle, a matrix, in a non-commutative geometry, you should use trace dynamics. So that is the parallel. In arriving at non-commutative geometry, Cohn's non-commutative geometry, the idea is that you first map the geometry to an algebra, a commutative algebra, raise it to a non-commutative algebra, which is again like, changing C numbers, say, to matrices. You see the parallel with trace dynamics. So make the algebra non-commutative. Then it's important to remember that the information about the algebra, for instance, is in the spectrum. It's in the eigenvalues of the operators or the matrices, say the Dirac operator. Having made the algebra non-commutative, we think of there being an equivalent non-commutative geometry where analogous concepts, say, to Riemannian geometry or to symplectic geometry can be defined by always remembering this map from the algebra to the non-commutative geometry. What is the analogy with the trace dynamics? Let's start from a classical Hamiltonian dynamics in phase space. We know there is an equivalent Lagrangian dynamics. And what did we do in trace dynamics? We changed our degrees of freedom to matrices. Matrix valued polynomial Lagrangian, take the trace. So that is trace dynamics. So see the non-commutative process here. C numbers to matrices. Commutative algebra to non-commutative algebra. It's the same philosophy. And then we map it back to a phase space matrix dynamics where the matrices are resident in the phase space. So a non-commutative geometry will be assigned to now this phase space. That's what's going to happen in our theory. When we incorporate gravity, we will move over from ordinary phase space dynamics to a matrix valued phase space dynamics whose geometry will be a non-commutative geometry. That's what's going to happen. Okay, how are we going to do it? Incorporating gravity in trace dynamics. Let us start by writing the general relativity action. This is the Einstein-Hilbert action. We think in terms of Planck length square, which is proportional to Newton's gravitational constant, square root. LP square goes as G, that's true. Add to it relativistic point particles. This is ith particle. The action is mi integral ds, integrate over the trajectory, sum over all degrees of freedom. So here I take note to point out this fascinating fact that Einstein equations, despite being second order, are linear in the mass of the particle. This makes them more like the Dirac equation, which is linear in the mass, and that's a hint of the following kind, that the mass actually arises as a cross term. There are no terms like m square, unlike in the Klein-Gordon equation. This is like a square. It's like a square of the Laplacian. This is like gravity is acting on particles. So it's like grad times particle position. So the grad square, the Laplacian, but grad times particle trajectory. So this is clearly a sign of a cross term, It's like grad square plus grad times particle trajectory, plus we will add something like particle trajectory square. So we want to make this into a whole square, as we will see. Okay, how do we fish out from here in a useful way degrees of freedom for gravity, which are C numbers and which we can replace by matrices. So there is this well-known important theorem in geometry, also often known as the spectral action principle. Given a Riemannian spin manifold on which we have written this Einstein-Hilbert action, there exists the Dirac operator, the standard Dirac operator, I gamma mu grad mu, where grad is the covariant derivative on the manifold, includes the spin connection part. And we need a length scale to make this dimensionless, so we will work with Planck length as that length. The Einstein-Hilbert action is equal to up to a numerical coefficient, the trace of LP square dB square. dB is the Dirac operator. So one carries out what is known as the heat kernel expansion of the trace of the Dirac operator squared. It's an expansion in powers of 1 over LP4. The leading term, so in powers of 1 over LP square, the leading term is 1 over LP4, which is the cosmological constant term. We ignore that for the moment. And we stay up to order 1 over LP square. We ignore higher order terms. So under this approximation, trace LP square dB square can be written as the Einstein-Hilbert action, and further can be expressed as the sum of the eigenvalues of the squared Dirac operator. So trace LP square dB square is this sum, and hence the Einstein-Hilbert action is also this sum. Okay, what happens next? Let's go back and look at the full action. I will now substitute for the Einstein-Hilbert action in terms of these eigenvalues. So you see what has happened. The space-time volume integral has gone away. It's essentially been replaced by the trace or the sum of eigenvalues. This sum is standing in for integration over space-time. These quantities are now going to be those C number degrees of freedom, dynamical variables in the classical theory, which we are going to raise to the status of matrices or equivalently operators. So we are moving towards trace dynamics. We have taken a result from geometry, used it in general relativity, brought in these C number degrees of freedom, and we are going to convert them into matrices. And what have we done for the matter part? We essentially still kept it as such, just replaced this ds integral by a 4 volume integral over the delta function. If you carry out the delta function integration, you will naturally get the line integral back. Okay, we want to make a trace dynamics Lagrangian and a trace dynamics action. This object in geometry is known as the spectral action for gravity. But think for a moment, for a physicist, an action is a time integral, a volume integral of a Lagrangian. Where is the time in this? I'm going to take this C number degree of freedom, make it into a matrix. I'm going to take its trace. I'll get the trace Lagrangian. But what about time? Time is lost, you see, because we want to raise space-time to the status of matrices. That was the original goal. But of course, when you do that, you lose time. How will I do dynamics in the trace dynamics? This is where we appeal to a very fundamental result in non-commutative geometry. When we raise these C number degrees of freedom to non-commuting matrices, we are clearly into the domain of non-commutative geometry. Those matrices are not going to commute, and yet they carry geometric information. We are already in the domain of quantum gravity because the matrices are not going to commute. In non-commutative geometry, there is a beautiful result that the geometry possessive intrinsic notion of time flow. So that's what I call Cohn's time. Cohn's time is intrinsic to non-commutative geometry. So I read out in Cohn's own words what the time. He doesn't call it Cohn's time, of course. So he says non-commutative measure spaces evolve with time. In other words, there is a God-given one-parameter group of automorphisms of the algebra M of measurable coordinates, non-commuting algebra. It is given by the group homomorphism. This is a homomorphism from real numbers to a space labeled out M, which is the automorphism group, the set of automorphisms of the algebra modulo what are internal inner automorphisms. So in the trace dynamics language, you could think of inner automorphisms as the unitary transformations which do not change the trace. So what is Cohn saying? There is a God-given one-parameter group of automorphisms from the additive group R to the group of automorphisms classes of M modulo inner automorphisms. I discovered this fact in 1972, he says, when working on the Tomita-Takesaki theory, and it convinced me that there are amazing features of non-commutative spaces which have no counterpart in the static commutative case. This is from this article by Cohn's on the archive. You can also read more about Cohn's time in his own words in this blog. And for a deeper understanding, one would have to go and understand the so-called Tomita-Takesaki theorem, from where this result comes. From a physicist's viewpoint, we can do two things. We can accept Cohn's time as a given. It is definitely there. It's a one parameter family of automorphisms with labels which enables us to have a time in trace dynamics after gravity has been raised to the status of operators. More physically, we learn about it from the Adler-Miller charge. That is a conserved quantity. So I can think of phase flow as taking place in such a way that neighboring points which have the same value of the Adler-Miller charge are connected by the flow. So let's see what was the expression for the charge. I go back. So this is the charge. So in the phase space, I select a point. I find out what is the value of the charge there. I investigate in the neighborhood of that point and find out another point which has the same value of the charge. I connect these, and from the second point to the third point. So all these points which have the same value of the charge are now connected, and we can define flow, dynamical flow, as taking place along a trajectory, along that trajectory which preserves the Adler-Miller charge. So instead of saying that given Cohn's time, the Adler-Miller charge is conserved during evolution, we can say evolution takes place in such a way as to preserve the Adler-Miller charge. And that's one way of thinking of Cohn's time, which is adequate for us as a physicist. So we will assume that there exists in this new trace dynamics, the generalized trace dynamics, there exists a notion of a time which will be called time tau. And now we can proceed. So what do I do to this eigenvalue, the ith eigenvalue of the Dirac operator? I raise it to the status of a matrix. Which matrix? The very matrix of which it was the eigenvalue. So I replace the ith lambda I by the ith copy of the Dirac operator, and I hence introduce this new dynamical variable QBI, dQBI by d tau, 1 over L of that. L is a length scale I will associate with this degree of freedom QB, and I replace lambda I by dBi, the same operator of whose it was an eigenvalue. There's a reason, there's a motivation why we do this, because really we do the same thing in quantum theory. When we quantize, we say, let us replace the classical C number position C number by an operator. Which operator is that? It is that operator whose eigenvalue is the C number Q, which is the position. So we do the same thing here, replace lambda I by that operator of whose it is an eigenvalue. And we do this for every eigenvalue. Each eigenvalue becomes a new degree of freedom in trace dynamics. So what happens? Let's see. Lambda I will be replaced by 1 over L QBI dot. I forgot to put the 1 over L here. So QBI dot I square for the ith degree of freedom. Then you have to take the trace, the matrix trace of the polynomial, integrate it over Cohn's time. That is my trace Lagrangian and trace action for the ith degree of freedom. So there are these very large number of degrees of freedom of space-time and gravitation. So gravitation has also been brought in because it is hiding, it is out here. So these are gravitational degrees of freedom, or same thing as raising space-time points to the status of operators. But when you raise the point to an operator status, you lift the metric overlying the space-time point also. You bring the space-time point and the metric all together. We don't make a distinction between the manifold and the gravitation which overlies the manifold. We lift it together. This part is okay. This part is a little more subtle because, look at it here with these are matter degrees of freedom. QB dot I have already defined. Q dot Fi will be defined as that operator such that the eigenvalue of this operator is this object Mi integral. Okay, so one way to understand this is that we are taking this entire trajectory and replacing it by the corresponding operator which is defined by this. So that when spontaneous localization takes place, this operator will localize to this trajectory. And in fact, that is how space-time is emergent, because over here there is no space-time. Space-time emerges from spontaneous localization of fermionic degrees of freedom. When matter is made up of fermions. When matter localizes, space-time emerges. So that's the philosophy. Space-time results from collapse of the wave function of macroscopic objects. We don't talk of space-time in the absence of matter. To talk of space-time points and events in space-time, we need localized matter undergoing localized events along space-time trajectory. So that's the philosophy of this part. At the end of the day, we will define this as the action principle for one space-time matter degree of freedom. So this object you could call an atom of space-time, not matter, only space-time, because each eigenvalue has been made into a matrix. This is the trace dynamics Lagrangian. This is the action for one atom of space-time. When I add the matter part of it and replace this object by this object, I get what I call an atom of space-time matter, or an Aikyon. This is the action for the ith Aikyon. Notice that there is a sum over I. At the Planck scale, the universe is made up of enormously many Aikyons. If you want to think what is an Aikyon is an elementary particle along with the gravitational field it produces. That's the idea. We do not make a distinction between the fermionic source, say the electron, and the gravity which it produces, which is denoted by QB dot. So this will be the total action for one atom of space-time matter. The word Aikyon comes from the Sanskrit word Aikya, meaning oneness. It's oneness of space-time and matter. So hence an Aikyon. In the classical limit, this object goes back to this fellow. Of course, you can sort of sense it. QB dot square trace will go to one of the eigenvalues. Then I sum over the eigenvalues. I'll come here, provided I have explained how the cross terms QB dot, QF dot, how that trace becomes trajectory. So this trace localizes to one of the trajectories. The sum over all the trajectories gives space-time, and once I have space-time, each of these eigenvalues can be expressed as one particular trajectory. So the cross terms are the matter degrees of term, and now you can see why they are first order, because they are cross terms. The other square term is very likely what we'll get the Higgs boson out of here. So Higgs boson comes for free. This is true also for the non-commutative geometry standard model program. When you unify gravity and the matter degrees of freedom, and then the Higgs boson comes for free, so to say, because it's a part of the structure's additional degree of freedom. So these are a few of the references where you can see this discussion on the role played by fermions in the emergence of classical spacetime. So space and time as a consequence of Girardi-Rimini-Weber quantum jumps, space-time from collapse of the wave function, and here we actually proposed a quantum theory of gravity in trace dynamics using the ideas that I just described, and showed how spontaneous localization and emergence of space-time is actually a consequence of the underlying Planck scale trace dynamics. Okay. We can now move from this generalized trace dynamics at the Planck scale towards the newly proposed theory of unification using division algebras. So this is the proper way of writing the Lagrangian that we will be working with in trace dynamics to describe gravitation and fermions. So let's have a look at it. It's a trace Lagrangian, which is a product of two brackets, QB dot plus beta 1, then this square QF dot dagger, and a similar bracket, except that beta 1 is replaced by beta 2. QB dot describes space-time geometry. Remember, QB dot is the Dirac operator in the non-commutative case. This is the fermionic degree of freedom. This object describes an Aikyon. Everything here is dimensionless. Dot is a derivative with respect to Cohn's time. Cohn's time is scaled with respect to Planck time. Lengths are in units of Planck length. The Q's have dimensions of length. They are Grassmann matrices. Dot is a time derivative which includes a C factor, but with the understanding that c here stands not really for speed of light, but the ratio of Planck length to Planck time. The action s is divided by a constant which is having dimensions of action c naught, subsequently in the emergent theory to be identified with the Planck's constant h bar. This will be our working Lagrangian when there are only gravitation and fermions. There are many copies of this to make the entire universe at the Planck scale. And of course, we will be soon including gauge fields into this picture as we move towards unification. But before that, a few more words about this Lagrangian. We can derive equations of motion from here. We can write down the Adler-Miller charge, and we can show that upon coarse-graining, there are the two limits that we have already talked about. One limit is actually the sought for quantum theory, which does not depend on classical time. So quantum theory will emerge, but evolution will still be with respect to Cohn's time. That is the sought for quantum theory, which does not depend on classical time, which is what our goal was. It is also a quantum theory of gravity, and we in fact gave it a name, spontaneous quantum gravity. And if there is sufficient entanglement of the various degrees of freedom, spontaneous localization will result, giving rise to localized macroscopic bodies and an emergent classical spacetime. On that spacetime background, those degrees of freedom which have not undergone localization are still quantum. They can be described either via trace dynamics, or they can be described as quantum field theory on a space-time background. So that is the connection between the Planck scale matrix dynamics, the emergent classical space-time with general relativity, and quantum field theory. So quantum field theory on a classical space-time, curved or flat, as well as general relativity, are both emergent approximations to this underlying trace dynamics, where the universe is made up of many copies of such Lagrangians, one for each Aikyon. So notice that the underlying theory is actually deterministic. You can write down equations of motion. It's a deterministic but non-unitary theory. The emergent gravitational theory is in a sense a thermodynamic approximation to this. So is quantum theory. Quantum theory is an emergent phenomenon, and it is an emergent thermodynamic phenomenon in the sense that it has come out of a coarse graining of the underlying theory. If we are not watching or examining the theory at the resolution at which it has been defined in the first place, we are really doing statistical mechanics, and it is in that statistical approximation when quantum theory emerges. If the entanglement degree of entanglement is very high, classical space-time emerges. So both quantum theory and gravitation are at the same footing. They are emergent approximations, thermodynamic approximations, and in fact the quantum indeterminism arises as a consequence of coarse-graining. You can start with the deterministic theory, but if you coarse-grain it and do not observe the coarse-grained paths, you naturally get a theory which is not deterministic because you have lost information. And in fact, as we showed, that is also the origin of black hole entropy. This coarse-graining is where information is lost, so to say, inside the black hole, and that's the origin of black hole entropy. We actually give a proof that you get the correct entropy, Bekenstein-Hawking entropy, 1/4 of the area, by starting from many copies of the Aikyons. Okay, now we want to move towards unification. That's a interesting outcome, bonus of this theory. That's not what we started with. Let's remember our goal was quantum foundational, and that's how we came here. And now it turns out we can actually develop a very promising theory of unification with other interactions. So as I said, there are three fundamental constants in this Lagrangian: Planck length, Planck time, and a constant with the dimensions of action. So length, time, and action are fundamental units. There's no h bar in this theory. There's no Newton's gravitational constant, nor is there Planck mass. So h bar will emerge. Once h bar emerges, we can define Newton's gravitational constant in terms of Planck length, Planck time, and h bar, and we can also define Planck mass. So conventionally, Planck length, Planck mass, and Planck time are fundamental units. But here we turn the situation around. We retain Planck length and Planck time as units in terms of which lengths have to be defined, and a constant of action in terms of which actions are defined. So this is actually numbers. Everything here is numbers. That is a key reason why we can relate to division algebras, although we have bosonic degrees of freedom which are related to vectors, fermionic degrees of freedom which are related to spinors. We can bring them under the common platform because this is a dimensionless Lagrangian in action. So everything here is numbers. So we will naturally be led to quaternions and octonions. In fact, this object will be an octonion. This will also be an octonion. QB dot by itself will be a quaternion. Okay, so that's where we stand with before we go in towards unification. Now, there's a very fundamental reason why we must bring in gauge fields, and that is for understanding spin. See, this is trace dynamics. It's a complete dynamics by itself. How do I define spin angular momentum here? That definition must be there because mass essentially is 1/length. It's a parameter. But spin is not a parameter. Spin is a dynamical variable. It's angular momentum, canonical angular momentum. And I want to ask, what is that angle in this theory whose time rate of change is spin? In quantum mechanics, in relativistic quantum mechanics, we cannot ask that question because spin really is not a rotation in space-time. We know that. That rotation gives rise to orbital angular momentum. So it turns out to understand spin, we must first include Yang-Mills fields, and then we are naturally led from 4 space-time dimensions to 8-dimensional octonionic space, where it's very easy to understand spin. Okay, how do we bring in gauge fields? This is the prescription, very similar to what we do in quantum theory. To the Dirac operator, we add a potential term which has a one less time derivative compared to the Dirac operator itself. We add the potential for the Yang-Mills fields. So here we correspondingly add this term QB dagger in the first bracket. Alpha is the gauge coupling constant. To the fermionic part also we add, you could call it a fermionic potential, again the same coupling constant. Same thing in the second bracket, the same kind of substitution, except that of course here there is a adjoint, and yeah, I think there's a mistake here. No adjoint here. Adjoint only in the first bracket. Sorry about this. Okay, so we can make these replacements, and now out here we had 2 into 2, 4 terms. Here we will have 16 terms, yeah. Uh, this becomes 2, this 2 terms here, 2 plus 2, 4, 4 4 is the 16. So we can open out the Lagrangian, or we can write it in a much nicer compact way by defining these variables q1 and q2 like this. q1 is qb plus beta 1 qf, q2 is qb plus beta 2 qf. We make this substitution out here after putting in the gauge terms, and we draw total time derivative terms. So there will be 16 terms here. Turns out that 8 of them are total time derivatives, and we assume that we can drop them. If you do that, then we can write the trace Lagrangian in this compact form. So the action part is still there. Inside it's like this, which is very nice. It's q1 dot dagger, q2 dot minus this potential term. So as if there's a kinetic energy kind of term. But notice it's not a square, it's a byproduct, as if we were describing a two-dimensional object, and it seems plausible that there's a connection with the string theory. Rather, you'd say that our theory is more general actually, because the Lagrangian is not self-adjoint. M theory possibly a part of this, in the sense that this object that we are describing is two-dimensional and it's evolving in Cohn's time. So it's like a membrane with a third time dimension. So it's not creating a world sheet, it's creating a world volume. And this object, which we will identify with an octonion. So it's an octonion, it's an octonionic space. The Aikyon is described by Grassmann matrices. It is like a membrane evolving in Cohn's time. So that is 3 dimensions, as if evolving in a 8-dimensional octonionic space. So 8 plus 3, 11. So there are a total of 11 space-time dimensions out here. This is an octonion, and that of course is reminiscent of M theory. So this is something like it's like the Aikyon is a membrane, it's a two-brane. And but as I said, this theory is more general because the Lagrangian is not self-adjoint, and more importantly, it's very easy to define and construct. This the Lagrangian is as simple as this. You can differentiate with respect to Cohn's time, write down the equations of motion. And as we'll see in the next few slides, this is the standard model plus gravity unified Lagrangian for one generation of fermions. It's very interesting that if we want to describe 3 generations, we are not allowed to drop the total time derivative terms. Once we bring them back, we can describe 3 generations. Without the total time derivative terms, we can describe 1 generation. It's not clear right now what is the role of the total time derivative vis-a-vis 3 generations. It looks as if something is happening at the boundary, at the upper and lower end of the time intervals, as if time is cyclic. That is one place where you wouldn't be allowed to drop the terms at the two ends. I mean, does that suggest a closed finite universe? That remains to be understood. So anyway, this is, as I said, the standard model plus gravity Lagrangian, as we'll argue, and it is clearly very simple. Okay, so where were we? That we bring in gauge fields in like this, and we are saying this will help us understand spin. Let's see how that happens. So in this recent paper, we actually give a basic dynamical definition of spin by first writing down the Lagrangian. So this is the same Lagrangian as here, with the gauge field replacement done. So that's 4 into 4, 16 terms. So here the time derivative has not been thrown out. We don't need the detail here. To understand spin, we define these variables q tilde b dot, q tilde f dot, these two new variables. And notice its structure. It's as if, suppose these are four space-time directions. These are four dimensions in the imaginary part. So, or if you think of this as one direction, this is the imaginary component of that. This is like the complex plane. We define a complex variable as if made up of two real parts, qb dot and qb. qb dot in fact is self-adjoint in our theory, qb is not. So you will make a qb dot dagger with qb dagger, and you will make a qb dot with qb. So think of this as if this is a 2D complex plane. So in terms of these variables, this Lagrangian, the Aikyon Lagrangian can be written like this. So you have a qb dot, you have a qf dot, and similarly here, again, describing a membrane as if. This is how we define spin. This is thinking of this as a complex variable. Again, introduce two new variables rb and theta b so that we can understand spin. This is like, these are bosonic matrices, these are fermionic matrices. Eta is a Grassmann number, so that this object is bosonic, and qf remains fermionic because Rf is fermionic. Define this amplitude and phase both for the bosonic as well as the fermionic degree of freedom. Then we have very natural definitions of momenta in this trace dynamics. The bosonic linear momentum as expected, fermionic linear momentum as expected. And now we have these new quantities, what I call the spin angular momentum. This is not a part of quantum mechanics. It's novelty, it's new now. The spin angular momentum is defined as the variation of the Lagrangian with respect to this fermionic angular velocity, similarly for the bosonic spin angular momentum, how do I imagine it? It's as if, you can see what this angle is doing, as if the Aikyon is rotating from the space-time direction to an internal symmetry direction. So I'm going to start thinking of this as the internal symmetry direction, and this the space-time direction. Spin is that angular momentum which results from an elementary particle rotating from the space-time direction to an internal symmetry direction. These definitions are independent of this particular form of the Lagrangian. All that is required that there be a gauge field which is thought of as the imaginary, lying in the imaginary direction, whereas the sort of gravity part is lying in the real space-time direction. Given this, irrespective of what the actual Lagrangian is, we can define these amplitude and phase variables, and here is the definition of spin. How do I know it is spin? We can look at this theory in the emergent approximation where this becomes quantum theory, and we find quite nicely, because of the properties of the Adler-Miller charge and its equipartition, when h bar emerges, this object is actually equal to half h bar, as we would expect for fermionic spin. This is integral multiples of Planck's constant. This can actually be proved. This is proved in this paper. So notice here, in trace dynamics, the spin is not quantized. It can't be. There is no h bar. So this is not quantized. In fact, there's a mixing. There's a mixing between bosonic and fermionic spins, and the conserved quantities come from all of these together. So there's a bosonic momentum including spin, which is conserved. There's a fermionic momentum including spin, which is conserved. Conserved in the sense that they're actually forces. This like Newton's laws. The time derivative of the momentum is proportional to the force, which is because of alpha. If alpha was 0, if the potential was not there, no force was there, then the momentum will of course be conserved. Otherwise it evolves. And in the emergent theory we get the same definition of spin as in quantum theory, and one can show that the conventional understanding of spin in relativistic quantum mechanics is actually recovered from here. And what is equally nice, we get a proof of the spin statistics connection because these degrees of freedom are bosonic. They by definition obey Bose-Einstein statistics because these matrices commute with each other. The state that you would make would be symmetric. Similarly, because these are made, the fermionic matrices are made up of odd-grade Grassmann variables which anti-commute. These quantities obey Fermi-Dirac statistics. So from statistics we derive spin. It's not the usual proof for the spin statistics theorem where we show that as a consequence of Lorentz invariance, we show that spin half integral particles obey Fermi-Dirac statistics and integral spin objects obey Bose-Einstein statistics. No, we actually show the other way around. Bose-Einstein statistics, integral spin, Fermi-Dirac statistics, half integral spin. So this, I think, is an important development. We wanted always an understanding of spin, and that comes from trace dynamics, provided you allow for this kind of a picture that just as there are space-time directions, there are internal symmetry directions equal in number, and in fact that's what leads us on to octonions. Okay, so from spin to octonions. So here is the internal symmetry direction. Here is the space-time direction. So if there's 4D space-time, naturally, because this is the QB dot is the time derivative of QB, it's evident that if you have 4 directions here, you'll have 4 directions here. You now have a 8-dimensional space in which a quantum system lives. The bosonic as well as the fermionic systems both live in 8 dimensions. The Aikyon lives in an 8-dimensional physical space. So physical space is 8-dimensional. It is inevitably non-commutative because these degrees of freedom do not commute with each other. Then it is the most natural thing that comes to mind is the space, octonionic space. Think of this just as, there's R4, say, a space-time manifold, which is defined by real numbers. Or I could think of a space made up of complex numbers, just like the complex plane, one can think of it as space having a geometry. We also have quaternions, it's a 4-dimensional space. Similarly, we will assume that this space in which, say, the electron lives, or in which the bosons also live when treated as quantum systems, that space is 8-dimensional. Turns out it won't be a space-time, it would be actually a phase space, what is known as a two-plectic geometry. So this is a Riemannian manifold, but this object, this 8-dimensional space, behaves like a non-commutative phase space. what is known as a two-plectic geometry, which has a invariant three form, essentially having to do with the fact that we are constructing world volumes for the evolution of a membrane. So the Aikyon is a membrane evolving in Cohn's time in this 8-dimensional phase space. Also, look at this. The way it comes is the velocities, and as if these were configuration variables, already suggestive of, the phase space, except that the geometry is not a symplectic geometry. It is what's known as a two-plectic geometry. More on that in a moment. Okay, so the angle which was changing when we defined spin is this angle. If you think of quantum systems as living in space-time, you would never know that this angle even existed. We are always thinking of an electron as existing in space-time. If the state is in Hilbert space, but the particle is in space-time, and that leads to puzzles. Now, for once and for all, we give up the idea that the electron lives in a space-time. The electron lives in a 8-dimensional octonionic space, evolves in Cohn's time, and that it is really a membrane. And people who study two-plectic geometries actually construct what are called two Hilbert spaces in a pre-quantum theory. So one can properly define a Hilbert space in which the state lives, and the physical space in which the particle lives. Okay. So this I have already described. Now the beautiful thing happens. There is a Octonionic algebra in this 8-dimensional space. Basically, automorphisms which map one set of coordinates to another set of coordinates in Aikyon. These take the place of general coordinate transformation, space-time diffeomorphisms, and they also take the place of internal gauge transformation. In the conventional theory, internal gauge transformations are taking place along this internal symmetry directions. Space-time diffeomorphisms are taking place along these 4 directions. But now we unify that concept into 8-dimensional algebra automorphism. So that's unification. That's a geometric unification, except that we won't be anymore having we won't have a 8-dimensional Riemannian space-time. We'll have a 8-dimensional two-plectic geometry. It's a non-commutative geometry. So we may now replace general covariance and gauge invariance by saying physical laws are covariant under algebra automorphisms in this 8-dimensional octonionic space, and this Lagrangian is actually a manifestation of that. We will consider only those unitary transformations which are generated by the generators of these algebra automorphisms. So not all unitary transformations are permitted. Only those which are compatible with these algebra automorphisms are to be allowed. So you see, that's beautiful. That determines the symmetry group, the unitary group of the theory. Why is it why, for example, is there SU3 or SU2 weak or U1 electromagnetic? All those will come out as consequences of the following fact, that the automorphism group for the Octonion algebra is the smallest of the exceptional Lie groups G2, which has 14 generators, and that contains within itself as subgroups SU3, SU2, etc. The symmetries of the standard model are no longer invented by hand or dictated by experiment. They are dictated by the fact that the Aikyon necessarily lives in an 8-dimensional space. And how did we land here? Because we wanted to understand spin. So in that sense, the construction is very fundamental, axiomatic. Now, why this particular Lagrangian? So this is the one that is here with the total time derivative terms dropped. So instead of 16, you have 8 terms. And what is this object is now an octonion. QB dot has, as it had so 4 space-time directions, so this also 4. This object is an octonion. Its dagger is also an octonion. This object is an octonion. Okay, so we'll remember now that we can make an octonion from the fermions. We can make an octonion from the bosonic degrees of freedom. In fact, we can do even differently. At some stage, we right here, yes, you can combine bosonic and fermionic degrees of freedom, and again make it. This is an octonion. This is an octonion. There are different ways you can combine bosons and fermions and make an octonion, or you can combine just bosonic degrees of freedom and make an octonion. Okay, that reminds us that we must make note of the fact that suppose I look at this Lagrangian, I can, just because of the fact that it is a square, it may be easier to see here. If I interchange bosonic and fermionic degrees of freedom, that is, define a new QB dot prime which is equal to this object, define a new beta 1 QF dot prime which is equal to this object. So you have actually interchanged fermionic and bosonic degrees of freedom without changing the Lagrangian of the theory, and that certainly is a supersymmetry. The Lagrangian is almost trivially supersymmetric, except that it will not generate any new superpartners. The number of bosonic and fermionic degrees are equal, and it turns out that the known bosons and fermions in effect are superpartners of each other. Before symmetry breaking, say everything is massless, and then mass is acquired as a result of spontaneous symmetry breaking. The number of known bosons and fermions does not have to be equal. What is equal is these degrees of freedom from which bosons and fermions will be defined. So this is a supersymmetric theory. It hence possibly solves the hierarchy problem, because you can talk of a 0-point energy which will cancel between bosonic and fermionic degrees of freedom. And furthermore, there is it looks like there is also let's look at this one. There's a gauge gravity duality, because this is the space-time gravity part. This is the internal degrees of freedom part. It comes with alpha. You can now again interchange. You can redefine a QB dot prime, which is QB dagger, and a QB dagger, which is QB dot, a QB dagger prime, which is QB dot. So there clearly is also a gauge gravity duality, simply because of the nicely symmetric way in which the Lagrangian is constructed. Okay. So this is that same Lagrangian from which the total time derivative terms have been dropped. Now we will, building on Cohl Furey's work, we will argue that in the potential energy part, these terms are related to what she called the electrocolor symmetry. So what is the nature of these terms? There's a potential energy term for these internal degrees of freedom. It turns out that these describe the strong force and electromagnetism. And this is the interaction action of the gluons and the photon on the fermionic degrees of freedom. These two terms, we argue, they actually correspond to one Higgs boson. So you're labeling these terms T1, T2, T3, T4, T5, T6, T7, T8. T8 terms for one generation of fermions. We'll come to 3 generations later. This part, this is the new finding in this paper. This is already known from Cohl Furey's work, that one can relate the electrocolor symmetry to octonions, the division algebras. Now, this is the new find that the weak symmetry, the weak interaction, is not internal symmetry with the coupling constant. Rather, it comes with the gravitational part, or what we call the Lorenz symmetry part. And many people have long suspected that the weak interactions is actually a space-time symmetry, or perhaps a space-time symmetry as well as internal symmetry. So that's sitting here. That's what we'll argue now in this paper. That's a new development. So these three terms for the Lorentz-Weak symmetry, these two terms for the Higgs boson, and these three terms for electrocolor symmetry. So for one generation of 8 fermions, plus the gluons, the photon, the weak bosons, and what we will introduce as a new particle, the Lorentz boson, they are all described by this Lagrangian. The unitary symmetry will be the one generated by the generators of this group G2, which has 14 generators. Those 14 generators are identified with the 14 bosons of this theory, constructed from these QB dots and QB and QB dagger. Okay. So the rest of the talk builds on, is based, aimed towards describing this identification. Why is this the electrocolor interaction? Why is it the Lorentz-Weak? And then, of course, we have to stop thinking in terms of parts. There has to be a total symmetry group and a unification. That symmetry group is G2. So that is a unification of the 4 forces for one generation. The unified theory is described by this Lagrangian, which describes elementary particle and its interactions. For example, if this is the electron, this is the Lagrangian for the electron Aikyon. Similarly, another manifestation of this very Lagrangian would be the neutrino Aikyon. So all the different particles and their interactions are different manifestations of this Lagrangian, and their properties are dictated by the Octonion algebra. So the very fact that the particle is living in a non-commutative octonionic space restricts what kind of properties it can have. Charge quantization, the fact that there are 6 quarks and 2 leptons per family, actually is a consequence of the Octonion algebra. That's a great achievement of Cohl Furey, building on the work of other earlier people like Gunedin and Gursi and others, is showing that the algebra dictates the properties of the particles, and it's also a dream expressed by many physicists and mathematicians, including Michael Atiyah, who opined that fundamental elementary particles will one day be understood in terms of the properties of these beautiful numbers, these 8-dimensional numbers, octonions. And one could claim that today we have essentially reached that goal by introducing this Lagrangian in trace dynamics. Trace dynamics, non-commutative geometry, and division algebras, they talk to each other extremely well, and it's in fact very straightforward to understand the standard model and its unification with gravity once you are in this framework. Okay, so I call this standing on the shoulders of giants because, without these papers, which have come out just in the last 3 or 4 years, it would be impossible to arrive at this conclusion as to what this Lagrangian is describing. So Furey, Stoica, Dubois-Villette, Todorov, Drenska, Gillard, and Gresnik. Building on earlier work in the last 3 or 4 years, all these researchers saw the significance of octonions, the Clifford algebras, CL4, CL6, and these exceptional Lie groups G2 and F4, and the exceptional Jordan algebra J38. They come very close to describing the standard model and Lorenz symmetry in terms of division algebras and Sedenions and this exceptional Jordan algebra. What they were lacking is a Lagrangian which would do justice to these studies, because without the Lagrangian you can't have dynamics with just division algebras. And similarly, our work, we have a Lagrangian, but in order to arrive at the standard model, we must make contact with their studies on division algebra. So trace dynamics and the study of division algebras and standard model, they complement each other. Their coming together, I think, is an important development as we move towards a unified theory. Trace dynamics at the Planck scale plus 8-dimensional octonionic space. And in that, the Aikyon, which is a two-brane, evolves in Cohn's time. Very important development in particular is the study of the maximal subgroups of G2 and their intersection, and the fact that there are 3 copies of the Lie group G2 in the next larger Lie group, exceptional Lie group F4. These maximal subgroups play a very important and beautiful role in understanding how the 4 interactions come about and get unified. Okay. So for some time now, a couple of slides, I describe Cohl Furey's work and how she is led to relate the standard model to octonions. So given the algebra of complex quaternions, and OTH, which is SO3, this is the automorphism group of the algebra of quaternion, that is SO3. That is why quaternions were invented by Hamilton to describe rotations in 3 dimensions. He realized he needs 4 degrees of freedom, not 3. From here you can make the Clifford algebra CL2 and the SL2C algebra, which describes the Lorenz symmetry. Why do we even study it? To see how similar the Lorenz symmetry is to the internal symmetries, especially the weak symmetry, we will start thinking of the Lorentz transformation in the same way that we think of gauge transformations. And just as gauge degrees of freedom describe interactions, we'll think of the motion and the rotations in space-time, or the translations in space-time generated by the Lorenz group as actually an interaction. We have to think of motion also as if it were an interaction mediated by the newly introduced Lorentz boson. So complex quaternions, their generators of their algebra can be used to make the group SL2C, which gives a faithful representation of the Clifford algebra CL2. You can make this pair of fermionic ladder operators given a quaternion with the real direction E0 and imaginary directions E1, E2, E4. You can make these fermionic ladder operators which form the Clifford algebra because the standard conditions of the algebra are satisfied. Then you can form the idempotent, the projector, from these ladder operators. The action of these generators on the idempotent and on its complex conjugate V star gives what are called minimum left ideals. These are the left and right-handed Weyl spinners, and these now in our theory will acquire the status of quote-unquote Aikyons, special cases of Aikyons. Why we say that way? Because a similar algebra CL6 the Clifford algebra CL6 constructed from the Octonion algebra, which describes quarks and leptons. So if CL6 describes quarks and leptons, CL2 in a sense will describe the Lorentz boson and the accompanying Higgs particle. So what is the connection with the Lagrangian? So this is going to be the electrocolor part, gluons and the photon. The so-called Lorentz boson is hiding in here. These are four components. So together they will define the weak boson, the three weak bosons, the weak isospin, the Higgs boson, and the Lorentz boson. So that's the Cl2 in a sense is hiding here. Actually, it's a part of a Cl6, something like a Cl2 cross Cl4. Cl2 plus Cl4. Okay, so we come back to that. So this is the construction of the Clifford algebra Cl2 from complex quaternions. As I said, why is it interesting? Mainly to show how similar the description of quarks and leptons is to this description of the Weyl spinors. Okay. Now, because the Aikyon lives in the octonionic space, the algebra of complex octonions becomes very central and important to us. So we describe the work of Furey in her PhD thesis and recent papers, and also parallel work by Stoica, who construct actually two copies of CL6, one for the electrocolor symmetry and the other one for the weak symmetry and the Lorentz symmetry. So we know that because the octonions have a non-associative algebra, they cannot by themselves give a faithful representation of a Clifford algebra, in particular not of CL6. So what Furey proposes, building on the work of Ablamovich, is to construct octonionic chains. So these are maps, basically maps of octonions onto themselves. You can make what are called octonionic chains, and they have the properties of a Clifford algebra. So these chains actually they have 64 degrees of freedom. So they can be used to construct a 64-dimensional basis, which is equivalent to 8-byte complex matrices. And this basis gives a faithful representation of CL6. So CL6 can be made using these octonionic chains. Basically, how do you come about that? The octonion, of course, has 7 imaginary directions. But if you restrict the automorphisms of G2 to the element preserver subgroup SU3, one can make a CL6 using 6 fermionic ladder operators made from 6 out of 7 octonion imaginary directions. So E1, E2, E3, E4, E5, E6. Leave out any one direction, E7. So you have 6 directions using which you can make 6 fermionic ladder operators which satisfy a Clifford algebra CL6. So we make note of this. What did we do? What is the element preserver subgroup of octonion? So suppose you want to consider only those automorphisms which would leave an element out. So suppose you left out E7, you make automorphisms with the other 6, but you want to keep only those automorphisms which will always keep E7 out. So such automorphisms can be shown to form a group which is SU3. This is a part of the Octonion algebra. It's called the element preserver subgroup of G2. It's very important so we keep that in mind. If you restrict the automorphisms to this SU3, you can make a CL6 from the octonionic chains. These ladder operators, when they act on the idempotent V is defined very similar to what was done here. When these act on the idempotent V, these give minimal left ideals, which now span an 8-dimensional basis, not the full 64-dimensional basis, an 8D basis made from 3 ladder operators and their adjoints. So, it's easy to see how from 3 ladder operators and their adjoints you'll get a 6 to 8-dimensional basis. Under transformations of SU3 cross U1, this is basically it's U3. There's a U3 symmetry that these ladder operators have, and U3 you can write as SU3 cross U1. Under these under automorphisms belonging to this group, under unitaries belonging to this group, elements of this basis, you act on the idempotent, you generate a 8D basis. Elements of that basis transform under these unitaries the same way as do one generation of 8 quarks and leptons. What does this mean? That 3 of those elements in the basis, they transform amongst each other as anti-triplet, another 3 as a triplet, 2 of them transform as singlets, already suggesting the presence of 6 quarks and 2 leptons. Then you construct the charge operator from the number operator. Just as is idempotent, you can make the number operator alpha dagger alpha, and here of course you sum over 3 degrees of freedom, so you have a number operator made from 3 sets of alphas. The charge, the electromagnetic charge, is defined as n by 3, where n is the eigenvalue of the number operator, and lo and behold, you find that these 8 basis elements have charges of 0, 1/3, 1/3, 1/3, 2/3, 2/3, 2/3, and 1. So we immediately see the emergence of a quantized electric charge, and because of the transformations under SU3, the correct behavior for 8 quarks and leptons. So that's where the identification with the elementary particles, 8 fermions, 8-dimensional basis generated by this Cl6 acting on the idempotent. So elementary fermions are identified with minimal left ideals made using Cl6 inside octonions when you restrict it to this element preserver subgroup. Now, of course, we want to think of elementary particles as living in a physical space. We don't want to give them just an abstract definition as minimal left ideal. So we can, that's where our Lagrangian comes in. So this is our Lagrangian, right? So we want to make a map between those minimal left ideals and this Lagrangian. And the way to do it, that there is a 64-dimensional basis, which is the representation of Cl6 made from the Octonion algebra. You map these 64 degrees of freedom to 8 by 8 matrices. Now these are not just complex matrices. The entries are complex Grassmann matrices, QF, fermionic matrices. So 8 by 8 matrices, each entry in that matrix is itself a fermionic Grassmann, a complex fermionic Grassmann matrix, and identify the 8 quarks and leptons with 8 corresponding QF. So what do? We are saying that these QF are to be identified through a map with those minimal left ideals. Those were, elements of the octonionic chain. They are mapped onto 8 fermionic operators, and that's how we get the identification say of an electron with the fermionic operator. Similarly, the, the bosonic degrees of freedom there are the generators acting on the idempotent which gave the basis. Those can be identified with these QBs. So hopefully that now makes it clear. What does this Lagrangian have to do with Furey's work? So because there's a map between those basis elements, those 8 basis elements, with the corresponding QFs and the generators, the corresponding QB, this object will have the same transformation properties under SU3 cross U1 as did those basis elements. And so that in a sense is the connection with this Lagrangian. To put it differently, notice here that here are these terms made exclusively from fermions. So when we say that Furey uses the Octonion algebra to describe these elementary particles, we could ask, why do elementary particles need the Octonionic algebra? The answer lies here in this Lagrangian. These degrees of freedom are residing now in an Octonionic space that is dictated by understanding of spin. They are described by this Lagrangian, which is describing an Aikyon in 8D Octonionic space. It has terms like this, which is basically these are terms made exclusively from fermions. So we can say we want to know what is the algebra of these octonions. So to understand that, to understand the properties of elementary particles described by these actions of octonions on themselves, is why Furey has to do this. You see, that's what you're saying. Division algebras historically came before the Lagrangian, but now we can say as if the Lagrangian was already there, as if this Lagrangian was already there, and this object is living in an octonionic space. You have no choice but to ask, what are the constraints imposed by the Octonion algebra on the properties of the particles? And these are the constraints. They behave, these terms in the Lagrangian behave exactly as would do 8 quarks and leptons of one generation. The quantization of charge is achieved precisely because of the algebra. That is beautiful. Either it is coincidence, which seems extremely unlikely, because now we even have a Lagrangian which describes the standard model length unification with the Lorenz Symmetry. So we can say that we were studying that Lagrangian, and that's how we realized that these constraints come about. Okay, so we said the connection with the Lagrangian is that we map the 64 degrees of freedom to 8 by 8 matrices whose entries are the complex Grassmann matrices QF. We identify 8 quarks and leptons with 8 corresponding QF. And we identify the 9 generators with, 8 for gluons and 1 for the photon from the number operator. U1 is defined from the number operator made from the SU3 generators. These are to be identified as the 8 plus 1 bosonic degrees of freedom, 8 for gluons and 1 for the photon from the number operator. So we conclude terms T5, T6, C7 describe one fermion generation under SU3 cross U1. So SU3 cross U1 are the allowed unitaries you can make on this trace Lagrangian. And why only those? Because that's dictated by the Octonion algebra. There's one thing, important fact I forgot to mention. It is known from the work of Cartan that the Lie algebra of G2 has a symmetric invariant bilinear form. This is a scalar. x0 square plus x1 y1 plus x2 y2 plus x3 y3. So this Lagrangian, interestingly, turns out to have just that form. It's like x0 square, x1 y1, x2 y2, x3 y3. Provided you restrict to only 1/2, or it's like setting alpha equal to 0. Or if you ignore this and you just look at this part, this is again like this, x0 square, x1 y1, x2 y2, x3 y3. So 1/2 of the Lagrangian, either the Lorentz-Weak part or the electrocolor part, has, and when you take its trace, has precisely the form, same form as this invariant bilinear form. So we will restrict ourselves to only those unitaries which would have kept this form invariant in the sense of the Lie algebra of G2. We are not allowed all unitaries, though only those unitaries which are generated by G2 and which will keep this form invariant. And that is how we come to understand why the standard model is described by these particular unitary symmetries, because those are subsets of G2. And why only 1/2, that we come to now. We'll find that G2 can either describe electrocolor or it can describe Lorentz-Weak. It does not have enough freedom within itself to describe both. You can make only one CL6 from G2, cannot make two. That CL6 is used up for here. If you didn't use it here, you can use it here, as we will now show. So if we want to describe the whole Lagrangian, we will have to move on from G2 to F4. That we'll see shortly. Okay, so this is where we were. This is what the work of Furey and also of Stoica. That you building on their work, we show that these three terms in the Lagrangian describe one fermion generation under this group. Two of the other terms in the Lagrangian possibly describe one Higgs boson, and there are three remaining terms. We have to somehow figure out what do these terms have to do with the weak interaction and with gravity. That is not clear from here. We have only got electrocolor SU3 cross U1. What about the rest? What about the weak interaction? Okay, so that brings us to the work in our present paper, introducing the Lorentz-Weak symmetry and prediction of the Lorentz boson. As we said, the Octonion algebra can give only one inequivalent faithful representation of CL6. How do we describe the SU2 weak symmetry what about the first three terms? It turns out, now this gets very interesting, that one must pay attention to the maximal subgroups of these exceptional G groups. G2 is the automorphism group of the algebra of octonions. It has two maximal subgroups. One is the element preserver group of the octonions, SU3, that is already utilized by Furey. It turns out there's another maximal subgroup of G2, which is the stabilizer group of the quaternions inside the octonions. That group happens to be a SU2 cross SU2. What is a stabilizer group? Those automorphisms which acting on quaternions will send them to other quaternions. So that's a stabilizer group. Of course, quaternions by themselves have their own automorphism group, that is SO3. That's not what we are talking on. If you are inside SO3, quaternions will go to quaternions, but turns out there are other automorphisms which will send quaternions inside the octonions to other quaternions, and that's the stabilizer group. That is this group, and now this plays an equally important role as SU3. If we first look at some of the further properties of these two maximal subgroups, they have a U2 intersection whose normal subgroup is SU2. We'll see this in a diagram in a more picturesque way. These two subgroups, SU3 and this one, they have a U2 intersection which is SU2. This SU2 is also a subgroup of the stabilizer group of octonions. Named, and what was that? The stabilizer group by this. This SU2 is also a subgroup. But I mean, it's a subgroup of the element preserver group. That's what I wanted to say. The intersection, there's a U2 intersection whose normal subgroup is SU2. It's also a subgroup of the stabilizer group of, this should be quaternions. This SU2 is a subgroup of this, and it is the element-wise stabilizer group of the quaternions. Just as the octonions have a element-wise stabilizer SU3, the quaternions also have an element-wise stabilizer group, and that happens to be again this SU2, and SU2 is also a subgroup of this group, which is the stabilizer group of, this should be quaternions. And the stabilizer group of the octonions is the group, again it should be quaternions. The stabilizer group of the quaternions is the group extension by SU2 of the automorphism group of quaternions, and this is SO3. So if this is causing confusion, let's come here. This diagram is much better. We can stare at it for some time. Let us imagine that this is the space which represents the automorphisms of the octonions. This is the group G2. It has two maximal subgroups, this one and this one. This is SU3 cross U1, the element preserver group, element-wise stabilizer or the element preserver group of octonions, SU3, and then extended to the number operator U1. This describes the symmetry of the electrocolor symmetry of the standard model, for which we made a Cl6, one generation of quarks and leptons. Then there is this group stabilizer for auto-H, those automorphisms which will send quaternions to other quaternions. This SO3 is the automorphism group of quaternions. Its group extension is this SU2. So these two have an intersection. These two have a U2 intersection, which is SU2 cross U1. This SU2 is also a normal subgroup of this SU2 cross SU2. So you can possibly see where we are getting at. It turns out you can, if you did not make a Cl6 corresponding to this element-wise stabilizer, you can make a Cl6 corresponding to this group stabilizer of the quaternions. That has the correct symmetry properties, correct transformation properties, as if it was describing the weak interactions given by SU2, and a Lorentz symmetry described by the complexification of this automorphism group of quaternions, which will lead to a SL2C. So what we are saying, that G2 actually describes two sets of symmetries of the standard model, provided we choose to describe only one of them at a time. You can either make a Cl6 from this, or you can make a Cl6 from this, and this has the same symmetries then as the first three terms in the Lagrangian. So the Symmetry group for these three terms can be shown to be that SU2 cross SU2, which is why we are proposing that this describes a unification of the weak interaction with the Lorentz, which we call a Lorentz symmetry or Lorentz interaction. SU2 cross SU2, one SU2 for weak, or the weak interaction, the other XU2, then you have to complexify OTH to get an SL2C, which describes the Lorentz algebra. So this is the overall picture of what is happening inside G2. We must consider both the maximal subgroups as well as their interaction. So now you can see, and this is discussed in more detail in the paper, that how we came to this conclusion, building on Furey's and Stoica's work. The SU2 weak is behaving as if it is an internal symmetry, and it is also a space-time symmetry. This is space-time symmetry. This will lead to the Lorentz group. So the weak interaction is an extension of a space-time symmetry. At the same time, it is a part of an internal symmetry. It seems as if it is determined by electrocolor. So this is unification now. The Lorentz symmetry is unified with the weak interaction, which, for reasons which we don't understand fully, is a part of the electrocolor symmetry. So now we have a full unification, electrocolor, Lorentz-Weak, and that is exactly what is described by this Lagrangian. If you look at it all together, the symmetry group is the unitaries generated from G2, and the two maximal subgroups of G2 in fact has just the right amount of generators to coincide with the 14 generators of G2. So these degrees of freedom, QB dot, QB dagger, these are bosonic degrees of freedom can be used to make the 14 generators of G2, which together describe the Lorentz-Weak electrocolor symmetry. If you chose to describe it in parts, then if you set alpha to 0, then the Lorentz-Weak symmetry is here. The weak interaction is not an internal symmetry in the conventional sense. It's also, in hindsight, the right thing, because we know that the electromagnetic the coupling constant, the fine structure constant, and the strong coupling constant are both dimensionless, whereas the gravitational constant and the weak interaction Fermi constant both are dimensional. And in fact, if you put h bar equals 1, they have the same dimensions. So it's a puzzle. Why is the Fermi constant dimensional despite being an internal symmetry? And now we understand the reason. We understand it in this group theoretic sense, and it also helps us understand why the weak interaction, while its parity is just discussed in the paper in some detail, because it is a part of this Lorentz-Weak symmetry. And now, of course, we could ask, why call it Lorentz-Weak? Why not call it Gravi-Weak or Gravito-Weak? Because after all, we brought this QB dot to describe gravity. This is perhaps a little subtle and needs some more clarification in the future. One is essentially saying everything else here is the spin 1 vector bosons, the gluons, the weak isospin, or after they acquire mass, the weak the W plus W minus Z0. Why should there be a spin 2 object arising here? Of course, we want one of these will be the Higgs boson. The spin 0 Higgs boson also comes from here. So the three weak bosons, the Higgs bosons, and the Lorentz boson. So the claim is that it is much easier if we think of each Aikyon as having a Lorentz symmetry at the Planck scale, which is already it is evident here, because the symmetry group inside G2 is the automorphism group of quaternions, which leads to SL2C. So we see Lorentz symmetry. Where do we see gravity? Where there's no diffeom, there's no space-time diffeomorphisms here. It's very difficult to envisage that something here is describing a spin to graviton. So what is happening is that each Aikyon has a Lorentz symmetry, which is very good. It's good to have a Lorentz symmetry at the Planck scale. It makes life much easier. It helps us recover classical space-time of special relativity without having to worry unduly about where does causal structure emerge from a quantum gravity in which there is no expected causal structure, just because every Aikyon obeys the Lorentz invariance in its own octonionic space. And you have this structure for each one of the Aikyons. Spontaneous localization sends the Lagrangian of each Aikyon to different values, different eigenvalues of the Lorentz boson degree of freedom QB dot. Every Aikyon goes to a different value of QB dot. That in effect amounts to a gauging of the Lorentz symmetry. It's like, different tangent planes at different points in the emergent space together define a gauging of the Lorentz group, which amounts to gravity. So gravity is an emergent classical phenomenon which results from the spontaneous localization of a lot of Aikyons, whereas at the Planck scale there is no gravity. In this theory there is no gravity. There is only what you can call the Lorentz interaction mediated by the Lorentz boson, which is one of the bosonic degrees of freedom in this set. So this is strong and electromagnetism. This is weak and Lorentz symmetry. So we have sort of understood this diagram, and now this is a more precise description of the Lorentz symmetry using 4 generators borrowed, quote unquote, from electrocolor along with 2 generators from Automorphism. One can construct another CL6. So we can understand now why these generators can be borrowed, because this is sitting inside electrocolor. Electrocolor is this whole thing, I must say. It's not just this part that is electrocolor. SU3 cross U1 is this whole, this entire circle. That's SU3 cross U1. U2 and SU2 cross U1 are sitting inside it as a subset. Whereas on the right hand side, SU2 cross SU2, this whole circle, and the Lorentz symmetry and the weak symmetry are parts of it, and this is common between the two. That's why you can use generators of SU3 cross U1, which is what Furey did, and you see this in Stoika's work also. You can use these 4 generators made from electrocolor along with 2 generators from the automorphism group of the quaternions. From this part, that is, you can use these 6 generators to make another CL6 correctly, which correctly describes the action on one fermion generation of SU2 cross SU2 slash Z2, as if you were describing the interaction of weak symmetry and Lorentz transformations on an elementary particle. This you see in the work of Stoika also. He constructs 2 copies of CL6, but in hindsight we know that those 2 copies are not independent. They have an intersection, precisely the SU2. It can be considered an independent CL6 only if we set the coupling constant alpha to 0. So if the second part of the Lagrangian is ignored, you can say that I constructed a CL6 from here, I made a CL6 from the stabilizer group of quaternions. The first CL6 was made from the element preserver group of octonions, SU3. The second CL6 is made from the stabilizer group of the quaternions inside the octonions, but you cannot make two independent CL6. The Octonion algebra will give only one inequivalent faithful representation of CL6. You can use that either for electrocolor or you can use for Lorentz-Weak. You cannot do both. The symmetry group for the first three terms T1, T2, T3 in the Lagrangian is SU2 cross SU2 cross over Z2. It describes the Lorentz-Weak symmetry. So we are saying at the Planck scale, the Lorentz symmetry is unified with the weak interaction symmetry. We are not quantizing gravity. We are not unifying gravity with the standard model. We are identifying the Lorentz symmetry of an individual Aikyon with the, we are unifying that with the standard model internal symmetries. Okay, so we can talk a little bit more about the Lorentz-Weak symmetry and the Lorentz boson. So this is our Lagrangian. Actually, this is the Lagrangian for the pure gravity part. Remember what we started with before we added Yang-Mills fields. Here we see another reason how we motivate the Lorentz-Weak symmetry. So when we actually wrote down this Lagrangian, note there's no alpha here. This was just before we added gauge fields. We thought that this describes only gravity, but now we know better, you see. These terms include the weak interaction part also, which clearly comes out now as a space-time symmetry. We know that there is a second maximal subgroup, the SU2 cross SU2, which really describes the action of complex quaternions on the octonions. So you'll see what's happening here. This fellow is actually a quaternion. QB dot is a quaternion. Covers only the space-time, 2B space-time direction. So this Lagrangian is actually, the first three terms are actually describing the action of a quaternion on an octonion. So we have, Furey has considered earlier, complex quaternions, CL2, complex octonions, or CL6. We can now ask what happens if we consider complex quaternionic octonions. So that also one can anticipate. Again, there will be a associated Clifford algebra CL6 coming from this particular action, and that has this associated symmetry group SU2 cross SU2, which is what correctly describes this Lorentz symmetry, which also gives rise to chiral fermions. It explains why weak interactions violate parity because of this construction. In fact, it turns out in this theory the handedness change operator is charge conjugation, and the operation which takes the handedness change operation is complex conjugation. That's how you change spin, say from anti-clockwise to clockwise. You make a complex conjugation on these operators. Complex conjugation is also the operation which takes us from particles to antiparticles, and that's very interesting. It's as if it's telling us that the moment you make a particle into antiparticle, you automatically change the handedness, which helps understand why particles, why the fermions come with only one particular handedness, because that's the nature of this theory. So hopefully this will also help us understand better CP violation. So just to summarize, can make a CL6 from this action, complex quaternions on octonions, and that correctly describes the symmetries of the Lorentz-Weak interaction through these terms, which now we don't think of the first three terms of the Lagrangian. They are what are already there until you switch on alpha and bring in the gauge fields. We can open up this QB dot square expression, the bosonic kinetic energy, and here we see this predicted massless spin 1 Lorentz boson. It is this term, but we also have to figure out, and most probably that is already contained here from what we know already about the Lorentz fields, that there is also included here spin 0 Higgs boson and the 3 weak bosons. Together, the 14 generators of G2 are identified with 8 gluons, 1 photon, 3 weak bosons, 1 Higgs, that is 9, 12, 13, and the 14th one is this newly predicted Lorentz boson, which should be looked for in experiments. The Lagrangian has by itself has enough terms to possibly describe 3 more Higgs-like terms when we include 3 generations. So 1 generation, 1 Higgs-like term which is coming from here and its counterpart in the electrocolored symmetry. Okay. We must also make note of the physical motivation for unification of gravitation in the weak force, or Lorentz and the weak force. Only then can we understand why do weak interactions violate parity, because in this theory complex conjugation maps particles to antiparticles and also changes handedness, and we have a definition of spin. Because we can define spin, we are able to understand why the weak interaction violates parity. Without a canonical definition of spin, that would be impossible to understand. So we had to define spin, we had to identify the unified Lorentz-Weak symmetry to be able to answer this question. So clearly we are along the correct path. Why are the Fermi constant and Newton's gravitational constant dimensionful, whereas the electrocolor coupling is dimensionless? That question also is easily answered just by looking at the Lagrangian. There's a 1 by L square here. There was only a alpha square in the electrocolor part that was dimensionless, whereas this gravitation and the weak interaction will come out as dimensionful with a down by 1 by L square. So I interchangeably talk of gravity and Lorentz symmetry. Gravity is emergent from the spontaneous localization of a lot of Aikyons. So it is important that one must look for evidence of this gravity-induced modification of weak interactions. Because of this unification, we must look for this in experiments, and already a lot of thought has been put into this by Roberto Onofrio and Percacci and his collaborators, and other researchers have also talked of gravi-weak unification. It's not a new idea. It has certainly occurred to many researchers beforehand. It's just that we now are arriving at it in a sense from pre-geometric notions, first principles, and we have a proposal for a Lagrangian which makes this gravi-weak unification manifest. Now we move towards the unification of all the interactions, and what forces us there? Let's go back. Let's look at this diagram once again. This group G2 can be used to make a Cl6 which describes either the electrocolor symmetry or the Lorentz-Weak symmetry. It doesn't have enough algebraic structure within itself to describe all these symmetries together, and it certainly cannot deal with 3 fermion generations. I mean, our Lagrangian does not have enough degrees of freedom. This Lagrangian, if you each of QB dot together are one octonion and the fermionic part are another octonion, it turns out that this is 16 terms, 16 each, into it, 128 terms, 64 for the particle basis, another 64 for the antiparticle basis. That suffices to describe one generation of fermions. You need more. You need to go beyond G2 to describe 3 fermion generations, and that is why we say we need to go beyond. And also, there's a unification. Lorentz-Weak, electrocolor, they're all to come together, and we can't do that with a CL6. We need to go beyond the algebra CL6. So to describe 3 generations of fermions, it turns out that we have to move outside of division algebras to this next algebra in this Cayley construction, and that is going beyond octonions to sedenions. Turns out nicely though that our particles still continue to live in the octonionic space. What sedenions do is help us understand where the 3 generations come from, and there is also a connection of our theory to the exceptional Jordan algebra J38. To have enough degrees of freedom, we must bring back the total time derivative terms that we had dropped. So you can see the cross terms QB type times QB dot times QB, which we have dropped earlier, we bring them back now. So now we can count the terms. This is like one octonion, another octonion, so 16 directions, independent components here, 16 into 16, 256. This Lagrangian, now instead of 128 terms, will have 256 terms. And it turns out that this is the right number to describe 3 degrees of freedom, 3 generations, One generation we just saw had needed 128 terms in the Lagrangian. So 3 generations, one might think, need 384, which is more than this. What happened? Turns out very nicely that the Lorentz-Weak part is common amongst all the 3 generations. It's a space-time symmetry. Only the internal symmetries are different for the 3 generations. The space-time symmetry is common, and the Lorentz-Weak part had 64 terms. So 64 is overcounted 2 times. We don't need 64 into 3. We need just 64 into 1. So we must subtract 64 into 2, and very nicely the 128 into 3 minus 64 into 2 happens to be 256, which is very good. It gives us confidence that this is again the correct Lagrangian for 3 generations. Or to put it differently, the internal electrocolor symmetry requires 64 terms, the 64 into 3 for 3 generations, plus 64 for the space-time symmetry part. This also is 256. Each of the terms, so these are 2 brackets, the first bracket, the second bracket. Now that we have brought in the total time derivative, this is the sum of 2 octonions. It has 16 directions, 1 real direction which appears only here, 15 imaginary directions. That's the kind of assignment we make now, going past octonions. This is a sedenion. This first term is a sedenion, the second term is also sedenion. So now the Lagrangian has to be built in as if we have an action of complex sedenions onto themselves. We now look at the sedenion algebra. Turns out, mercifully, that the automorphism group of the sedenions is just the automorphism group of the octonions, G2, into the permutation group S3, which helps us to make 3 copies of G2 in the following sense. This takes us to what we now call the Aikyon theory for unification of standard model with gravity. The permutation group S3 is known to be isomorphic to spin 8. Spin 8 we know is related to SO8, which is famous for its triality, and that is what suggests that the Sedenion automorphisms are made from 3 copies of G2, 2 copies at a time, which is what is suggested from the intersection of subgroups of spin 8. That's a consequence of this so-called triality made use of by Gillard and Gresnik in their paper last year, and we just adapt what they did. So we are proposing that since our Lagrangian compels us to consider the Sedenion algebra, which is made up of 3 copies of G2 because of this permutation group, this possibly is an explanation for why there are 3 fermion generations, and we can understand that better from the relation between 3 copies of G2 and 3 copies of spin 8. That's what the triality and the permutation group are doing. G2 is the intersection of any 2 spin 7 subgroups of spin 8. There are 3 spin 7 subgroups. The intersection of any 2 of them gives a G2, and since there are pairwise intersections because of the triality, we get 3 such intersections and 3 mutually intersecting copies of G2. We'll see that in a diagram soon. Each copy of G2 has a subgroup SU3, which inside it has a subgroup SU2. This is already seen. This SU2 is the group extension of the automorphism group of the quaternions inside the octonions. Okay, so we are going to use this information to come to the unification diagram. Now, these 3 copies of G2 have to be embedded in a larger group, and that is F4, because spin 8 is a subgroup of F4. Spin 8 is giving these 3 G2 intersections, and the 3 copies of the Lie group G2 are embedded in F4, and we will see this important fact that F4, the Lie group F4, also happens to be the automorphism group of the exceptional Jordan algebra, which we'll see has a tremendous importance for our theory, as we'll see in a moment. Okay, so this is the unification diagram. We propose that the unification of the standard model with the Lorenz symmetry and hence with gravity is described by the group F4, recently studied very extensively by Todorov and Dubois-Villette. In their work, in fact, is an inspiration for us to draw this diagram. Inside F4, there are 3 copies of G2, which have a pairwise intersection and a 3-way intersection. A 3-way intersection is the group of automorphisms, AUT-H complexified. It has the Lorentz part of the symmetry. The Higgs boson will come from here. Interestingly, the electroweak part is sitting in pairwise intersection, and this should help us with a better understanding of CP violation. So essentially this is the unification. The electrocolor 3 copies, electroweak shared 2 at a time. The Lorentz group, the Lorentz symmetry, the Lorentz part of the Lorentz-Weak symmetry is a 3-way intersection. When under those conditions, just after the universe was formed, when sufficient entanglement takes place just below the Planck scale, the Lorentz part of the symmetry becomes the external spacetime symmetry because of spontaneous localization, whereas the others become internal symmetries. But we must remember the weak interaction part is somehow sitting in both the space-time symmetry part as also in the, as you can see, in the internal symmetry part along with the electrocolor. So this is 1 G2, one more G2, third G2. The SU3 color is here. And now when we think of unification, we should think of the full Lagrangian given here. This is the unification Lagrangian for 3 fermion generation as unification with the Lorenz symmetry. It has to be understood as a F4 rather than in parts. Okay, and so we can, given the Sedenions and their 15 imaginary directions, using 14 out of the 15 imaginary one vectors, we can make a Clifford algebra CL7 similar to how we made a CL6 from G2. There are 14 ladder operators which for the CL7 which when acting on the idempotent give rise to a 128 dimensional basis, another 128 for the complex conjugate basis, and for each of them, the V, the particle and the antiparticle basis, we can also we can have an interpretation of those 128 dimensional basis for 3 generations of 8 fermions each. Something similar was attempted for the unbroken SU3 cross U1 for 3 generations by Furey, the Octonion algebra. Now we moved on to the CL7. So these 128 likely do the following action. They have this interpretation. For each of the 3 fermion generations, 8 operations for the electrocolor that we've already seen, 8 for weak symmetry. So 8 fermions are introduced here. This basically defines the quarks and leptons, this basis. The other operations act on these basis elements, 8 for the weak interaction part, 1 per fermion, 1 for each quark or lepton, 8 for the Lorentz boson, and 8 for the Higgs boson. Yeah, so for each quark and lepton in a family, 8 for the weak symmetry, 8 for the Lorentz boson, 8 for the Higgs boson which accompanies this Lorentz boson, and that's 8, 8, 8, 8, 32, and we repeat that 3 times, 96 for 3 generations, the same action for each generation. That's 96. Then pairwise interaction, 8 actions between every pair of generations. So 8 per generation, 8 for the another generation, a pairwise interaction. 8 3s are 24. So this is 120. Another 8 possibly, this remains to be understood, for the action of the 3 Higgs from the terms T4 and T8. We haven't yet talked much about them. For every generation, there's a term T4 and T8 in the Lagrangian, and possibly on each of these for quark or lepton generation, these 3 Higgs are acting in a degenerate way, giving another 8 action. That would give a total of 128, another 128 for the conjugate basis. That explains what is happening in this 256 dimensional basis corresponding to the automorphism group F4. So that is the unification. We can give it some new name. Otherwise, we don't want to think now of Lorentz electro-weak color symmetry. It's all unified at the Planck scale. So whatever we call it, the symmetry F4 symmetry, let us say. Okay, where does the exceptional Jordan algebra come in? What is the connection with our theory, with our Lagrangian? Also known as the Albert algebra, J3O is the algebra of 3 by 3 Hermitian matrices with octonionic entries, and this is an element of the algebra. X, the function of xi and x, 3 self-adjoint components, and this is a Hermitian matrix. So these are octonionic entries, x1, x1 star, x2, x2 star, star is a complex conjugate, x3, x3 star. This has a characteristic equation, which is why we think this algebra is very important for our theory. This is a cubic equation. Because it's a 3 by 3 matrix. The cubic characteristic equation for x, trace x is as anticipated. Determinant of x can be worked out. It is given by this expression. This is what interests us most directly. This object s of x is bilinear in xi1, xi2, x3, x3 star. It is very similar in structure to our Lagrangian. We have not yet been able to show that our Lagrangian is exactly like this. We are working on that. Very likely the self-adjoint part of the Lagrangian, because these are Hermitian matrices, the self-adjoint part of the Lagrangian is likely to have this form. It will depend on this only one-dimensional parameter in the theory, alpha LP by L. That will enter this expression for s of x. It will enter in determinant x, it will enter in trace x. Most probably from here we are then likely to get a cubic equation for the dimensionless number alpha LP by L. And since this is since these are octonionic entries, possibly one cubic equation for every one of the 8 fermions. And this is nothing but, it's mass. 1 by L is mass and the coupling constant. We'll hope to get 3 real eigenvalues for this dimensionless quantity. We should eventually determine masses of elementary particles through this cubic equation. Then that would help fix the Higgs mass as well as standard model parameters. So that's why this characteristic equation is of great importance. It will complete the remaining part of the story, understanding the Higgs mechanism, the Higgs mass, where the masses of elementary particles are coming from. So there are 3 generations because there are 3 copies of G2 in F4. F4 also happens to be the automorphism group of the exceptional Jordan algebra. The exceptional Jordan algebra is very likely the algebra of the self-adjoint part of our Lagrangian. So everything is tying in very nicely. We just have to complete the remaining part of the project and see if we can successfully determine particle masses. If we do, then we have a successful theory of unification. If we don't succeed to do that, if we can't determine particle masses from here, then I think the theory will have to be ruled out. The structure is so watertight and everything is fitting in so beautifully within F4. You see, F4, where did we come to F4 from? We came from Sedenions, you see. If 3 copies of G2 were embedded in F4 because of spin 8, that is the natural embedding. We did not foresee that F4 is also the automorphism group of the Jordan algebra, exceptional Jordan algebra, which is related to the structure of our Lagrangian. So this is a pleasant surprise that the Jordan algebra also came in because of F4. Of course, there were octonions in our theory, we could have expected it, but this 3 by 3 structure clearly has something to do with 3 generations, and this hopefully carries the information about particle masses. Of course, one could immediately ask, the masses are going to come out near Planck mass because there are no small numbers in this theory. So this will be very close to Planck mass, a little more, a little less. What about the hierarchy problem? How are we going to get lower masses? So the hope is that trace dynamics recovers the emergent theory from coarse-graining over some length scale. You see, so that is up to us. What is the length scale over which we are going to coarse-grain? Possibly this has something to do with cosmology also. That's the evidence coming out of the theory that the cosmological expansion essentially stretches this L. So it is doing that in some particular way where it is preserving alpha by L in some sense. So if it stretches L, it is doing something to alpha also. So we ought to be able to predict the coupling constants at low energy as a running of couplings. We ought to be able to predict, possibly as a consequence of the cosmological expansion, what is the value of L at lower energies if it started close to Planck length at Planck's energy scale. So that is how we expect the roots of this cubic equation, which would be order unity, to scale down to lower numbers because of the coarse-graining as required by trace dynamics and because of the expansion of the universe. The masses are so much smaller than Planck scale because the universe is so much bigger than Planck scale, and there is evidence for supersymmetry in the theory. So the low energy theory is likely to be stable because of this inherent supersymmetry, but we must not expect to see any new superpartners. The known bosonic degrees of freedom are the superpartners, the known fermions, and vice versa. The only new particle we expect to see is the so-called Lorentz boson. Is there a relic Lorentz radiation on the same, in analogy to the cosmic microwave background radiation? How else should we detect the Lorentz boson? How do we detect the unification of gravity with weak interaction? Those are open questions for the future, but very likely this is a really promising approach to unification, and one could make a candid comparison with the string theory, the only other prominent unification theory. I think you can make a judgment for yourself how clean this theory is, how watertight and predictable it is. We predict so many things, and you see some more in the next few slides. So in comparison to string theory, where do we stand? It very likely the object that we have called the Aikyon is a two-brane. It's evolving in Cohn's time, so it has the self-adjoint part of our theory has some connection with M theory. The gain for us is that we gave up on quantum field theory at the Planck scale. We replaced it by the laws of trace dynamics, and trace dynamics is very easy to work with. You work with these branes individually. The Aikyons are branes. You can write down equations of motion in constant. So we gave up quantum field theory at the Planck scale in favor of trace dynamics. Quantum field theory is emergent. It's of course an extremely successful theory. It's the best theory for interactions that we have so far, but nobody told us that we need to extend QFT to the Planck scale. We give up QFT at the Planck scale in favor of trace dynamics for reasons that we have been discussing since the beginning of this talk. We bring in Cohn's time as for doing dynamics. We have given up space-time, so we need a new time, that is Cohn's time. Trace dynamics in Cohn's time, and the fact that understanding of spin forces us to octonionic spaces, then we are on to unification, we are on to F4 and Jordan algebras, all in a first principles axiomatic foundational sense. We did not take a string or a brane and say, let's quantize the string, let's quantize the brane. No. Why must we quantize? Our question was foundational, how to describe quantum theory without its dependence on an external classical time. That simple, deep, fundamental question has brought us here in a very axiomatic and logical manner, and the underlying theory is deterministic and non-unitary, that helps understand how quantum indeterminism arises at lower energies because of coarse-graining. So these are some important points which I have summarized, already said before. The Lagrangian is possibly supersymmetric, but no new superpartners. Possibly can solve the hierarchy problem. Possibly has a gauge gravity duality. Coarse-graining leads to the emergent quantum theory in Cohn's time. Because the Hamiltonian is not self-adjoint, critical entanglement separates Ortech, the SL2C made from here, the Lorentz group, leads to the emergence of classical spacetime and general relativity. So this is a reason why only the Lorentz algebra becomes a spacetime part, the rest become internal, because of the self-adjointness of QB dot. So this is discussed to some extent in this paper. The rest is under progress. Classical spacetime emerges because of spontaneous localization. Classical systems live in four-dimensional spacetime. We do not have to compactify extra dimensions. There is a great advantage over string theory and M theory. Because the underlying Lagrangian is not, underlying Hamiltonian is not self-adjoint, spontaneous localization is possible. So classical systems localize to four dimensions. Their existence in the internal direction is suppressed precisely because of the Hamiltonian not being self-adjoint. So two new elements gave up on QFT at the Planck scale. If we had QFT, we would have had to restrict to a Hermitian Hamiltonian, self-adjoint Hamiltonian. We have no choice. Those are the rules of quantum theory. If you have a self-adjoint Hamiltonian in 8 or 10 or 11 dimensions, you have this huge problem of what to do with the extra dimensions. You have to compactify them. The compactification is not unique. You get enormously many possibilities and you completely lose predictive power. String theory is unable to predict anything about the standard model precisely because it is sticking to quantum field theory on the Planck scale. It is sticking to a self-adjoint Hamiltonian. Neither of those two requirements are dictated by experiment. We have the freedom to shift to trace dynamics. We have the freedom to add a anti-self-adjoint imaginary part to the Hamiltonian. We must exploit that freedom. So no compactification. Dynamical, spontaneous localization makes classical systems live in four dimensions. The system descends from 8D to 4D because the anti-Hermitian part is forcing it to do so. Ortech separates from internal symmetries. As for quantum systems, they continue to live in 8 octonionic spaces. A quantum system does not live in space-time. We describe it approximately as if it is living in space-time. Its correct description is in the 8D octonionic space. As a result of our theory, we predict continuous spontaneous localization, the GRW theory. We also predict the collapse rate. It is given by a pretty formula, just LP by L cube over 1 over Planck time, where L is the Compton wavelength of the proton, and you can easily work out this is 10 to the minus 17 seconds. The proposed collapse rate of the CSL theory, we actually predict it from first principles. The difference from the most popular CSL collapse models is that the collapse rate actually now grows as cube of mass. It's a prediction of our theory. These are not mass proportional CSL models, and they are M cube CSL models, and that is a prediction. Once classical spacetime emerges, the uncollapsed quantum degrees of freedom obey laws of quantum field theory. Most close point of contact is the Stuckelberg-Horowitz formulation of relativistic quantum mechanics. We have shown that the Aikyon dynamics has a non-singular ground state. You can see this in this recent paper of ours. So this is a mechanism for avoiding the Big Bang and black hole singularity. We actually show that the Aikyon dynamics has a non-singular ground state of a finite width, finite area, in fact. The underlying dynamics is the deterministic matrix dynamics. Quantum indeterminism emerges as a consequence of coarse-graining. And we make a whole series of predictions. The theory is falsifiable, it can be ruled out. We predict the massless spin 1 Lorentz boson. Is there a relic radiation? No other new particles to be discovered if this theory is correct. If, say, a fourth generation of fermions is discovered, this theory will be ruled out. Weak interaction and gravity are related. This should be looked for in experiments. There is a Karolyhasy length uncertainty relation which any holographic theory of gravity must have. We predict that relation. We predict the novel phenomenon of quantum interference in time along with the GRW spontaneity. It's a prediction of our theory. GRW is a consequence of our theory. We predict that dark energy is a large-scale quantum gravitational phenomenon. We give an exact derivation of black hole entropy. We provide an understanding of spin. And we also explain this curious fact that the Kerr-Newman black hole has the same gyromagnetic ratio as the electron. The G ratio for the electron, as we know, is twice the classical value. That's understood from the Dirac equation. But if the Kerr-Newman black hole, the charged rotating black hole, is a classical solution of general relativity, why is its gyromagnetic ratio twice the classical value? We actually explain and prove that in our theory. So this is the outlook for the future, a summary, and what remains to be done. At the Planck scale, dynamical laws are those of trace dynamics. Standard model is unified with the Lorenz symmetry, not with gravity. The Hamiltonian at the Planck scale is not self-adjoint. Quantum field theory is emergent at lower energies. Gravity is an emergent classical phenomenon. Spontaneous localization causes the emergence of gravity. We do not quantize gravity. We only quantize the Lorentz symmetry at the Planck scale. Still to be worked out, the Higgs mechanism, particle masses, standard model parameters, and very importantly, what are the implications of Cohn's time for cosmology? This needs to be understood. So thank you for listening.